Now let's discuss the concept of a function. So, the general rule here is that a function is a rule or a correspondence relating two sets. One set is the input and one is the output, in such a way that each element in the input set corresponds to one and only one element in the output set. So for example, if let's say the input set here, let's call it X, and the output set here, let's call it Y, and you have elements in it. Let's say you have A, B, and C in X, and let's say you have D, E, and F in Y. So it says that the rule is that each element in the input set corresponds to one and only one element in the output set. So for example, A corresponds to D, and that is the only correspondence between set X, the input set, and set Y, the output set. So this is one correspondence, and let's say that B corresponds to E, right? But let's say that E corresponds to C as well. So the rule states that each element in the input set corresponds to one and only one element in the output set. So as you can see, A corresponds to D, B corresponds to E, and C corresponds to E as well. So each element in the input set corresponds to one and only one output in the output set. But let's say that you had another set, let's call it I, and let's call another output set J, and you have, let's say, elements like 1, 2, and 3 in the input set, and you have 4, 5, and 6 in the output set. But in this case, let's say that 1 corresponds to 4, fair play till now, but 2 corresponds to 5, and it corresponds to 6 as well. So that kind of negates the rule of a function that states that each element in the input set must correspond to one and only one element in the output set. But as you can see, 2 corresponds to more than one element in the output set. So this is not a function, and this is a function, right? So I hope that clears up the basic concept of a function. And so let me just rub all of this off. Now, the area, here are some examples of a function. The area A of a square. The A is the output, and it depends on one of the sides of the square, right? Because the area of a square is the length times the length of the square, right? So A is equal to x square, since one side is x. And that basically means for each each input of x is the input here, each input of x, that gives you a distinct value of A, right? So A is a function of x, right? For example, if you put 2 in place of x, that is 2 square, and that gives you 4. No other combination, no other value of x will give you 4 in the output. So it's a one-on-one correspondence. So it is a function. Similarly, for volume, you have the same concept over here, because all of this is just a constant. 4 by 3 pi is a constant, so you're left with R3. V is related to not R3, R cube. V is related to R cube, and for every single value of R that you put in, you have a distinct value for v, the output. So this is a function as well. Now let's see the formal definition of a function, and let's see what the domain of a function is and what the range of a function is. So a function f, let's say that the function or the correspondence, let's call it f, from an input set x to an output set y is a rule or a correspondence that assigns to each element x. X is an arbitrary name that we've given to every element in the set x. Each element in set x, a unique element in set y, right? The set x is called the domain of the function f, and the set y is called the range of the set of the function f, right? So you remember the two sets that are true, a and b, right? So each element in a and each element in b, right? And let's say this is a function, and basically the range of a, the set a is basically called the domain of the function, and the set y is the range of the function. And they have to be a set of real numbers, by the way. So here are some examples. You have this function that basically relates the output y with the input x, right? This whole correspondence is a cubic equation. And when you put x is equal to 3, then you have to find the range. That's the question. So this is how you do it. When you plug in x is equal to 3, you get 3 cubed plus 5 into 3 minus 2, and that gives you 40, right? So x is equal to 3 is the domain, and y is equal to 40 is the range. That's as simple as that. And I don't think there's really much confusion in this topic, because you just have to remember that the value of x is the domain and the value of y is the range. So yeah. Let's see the graphical representation of an algebraic function. It says that the graph of a function f in the xy plane is defined to be the graph of the equation y is equal to f of x. And y is equal to f of x because obviously the output y is to be related by some function, right? So let's say y is equal to 2x plus 3. This 2x plus 3 is the function that takes the input x to give you a value for the output y. So y is equal to the function of x, f of x. And so the graph of the function f is basically represented like this, and x is in the domain of f in the Cartesian plane, which is basically this xy plane, right? And basically you have ordered pairs like these that relate the input x to the output y. So for example, the input x here, let's say this point here, is at 2 and 3. So 2 is the input x and 3 is the output y. So this is the ordered pair. And so the graph provides a visual technique for you to determine whether the set of points represents a function or not, right? And if you remember that the requirement of a function is that one value of the input x, let's say this is the input set x and this is the output set y, one value in the input set must correspond to exactly one and only one value in the output set, right? So that is the requirement. And so naturally, if you have these two graphs, you can see that if you draw a line vertically from the x-axis, in this first graph, it gives you exactly 1 point of y, right? Look at this, 1 point in y. Look at this, 1 point in y. So this is indeed a function. But if you look at this one here, if you draw a line at this point, that gives you this point, and it gives you this point as well. So for one value of x, you get two values for y. And so this is not a function. The vertical line test is a very nice way for you to determine whether something is a function or not. Because writing this down, that's simple for very easy tasks. But when things get a bit difficult, you'll have to rely sometimes on the vertical line test, right? So yeah, the graphical representation, a very nice way to find out if something is a function or not. Now let's see algebraic, polynomial, and linear functions. So an algebraic function is basically any function that is defined by algebraic expression. So basically what that means is that it has variables like x, y, z, a, b, c, and so forth, Now you can classify them further into these categories. One is the polynomial function, right? The polynomial function is represented like this, basically. This is the general way of representing a polynomial function, okay? And basically these coefficients, the a terms, are real numbers, okay? And so they can be anything like 1, 2, 3, 4, 100, 200, anything, like any real number. And the exponents, basically these n terms, right, are non-negative integers. So when these two conditions are fulfilled, it is called a polynomial function. And the domain and range are subsets of real numbers, okay, for polynomial functions. If an is not equal to 0, which means an is the first term, basically, in a polynomial function, right? The first coefficient. It is a polynomial function of the degree n, and an is the leading coefficient, right? So an is basically the variable, is the coefficient whose variable has the highest power, right? So for example, if you have a function y is equal to 2x to the power 5 plus 3x plus 4 plus 2x squared. Let's say you have this, okay? So the variable with the highest power is this, x to the power 5. So this is a function of the degree 5, and the leading coefficient is, well, the coefficient of x to the power 5, which is 2. So the leading coefficient is 2, okay? So here's another example, right? So you have 2x to the power 4 minus 3x plus 2x minus 1. As you can see, the variable with the highest power is x to the power 4. So the degree is 4, and the coefficient of that variable is 2. So the leading coefficient is 2, okay? So let's see what a linear function is. If the degree of a polynomial function is 1, so basically the highest power of the variable x in the function is 1, right? Then it is called a linear function, okay? And it is the general form is this: f of x is equal to ax plus b, right? So you can see that x has 1 as its power over here, and a will basically just be the leading coefficient. I mean, there is only one coefficient over here, so it doesn't really matter. And a and b should be real numbers, okay? So here's an example: f of x is equal to 3x plus 4, or y is equal to 3x plus 4. It is a linear function, and its domain and range are again a set of real numbers. So that's basically it for algebraic functions and the two types. Now let's talk about rational functions and trigonometric functions. So a rational function r of x can be written down in this form. So basically r of x is equal to a function p of x divided by another function q of x, right? And both Px and Qx are polynomial functions. And Q of x must not be equal to 0. So these are the conditions. One, that P of x and Q of x are polynomial functions, and Q of x must not be equal to 0. In that case, it is called a rational function. And the domain of the rational function R of x is the set of all real numbers x. So basically all the numbers in the input set for which the function in the denominator is not equal to 0. So for example, if you had a function, let's say R of x is equal to 2x plus 3 over 4x plus 4, right? So the function in the denominator is 4x plus 4. Now when x is equal to negative 1, that would make the denominator equal to 0. So the domain of this particular example is basically all real numbers except x is equal to negative 1. Okay? So let's see what trigonometric functions are. So we denote and define trigonometric functions as follows. One is the function sine of x, and the graph for sine of x, once you plug in different values of x, is something like this, right? Again, graphical representations make things very easy. The maximum points are at y is equal to 1, and the minimum points, these dips, these valleys, are at y is equal to negative 1, which is why the range of this function is y lies between negative 1 and 1. But the range, the x values, can go on forever. So the domain of the domain is the x value, right? The range is the y value. So the domain is all real numbers, right? Similarly, you have cosine of x, and it has the same domain and the same range, because the only difference is that instead of starting at 0, this starts at 1. But it's the same as sine of x, right? Now you have y is equal to tangent of x. And once you plug in the values, you find out that the range for this particular function is all real numbers, but the domain is all real numbers except at these points, basically odd multiples of pi by 2, right? So you can just plot this graph, and this somewhat makes sense. Like, this is the graph, right? And it goes something like this. Now at these points, right, these are the points that are multiples of pi by 2, and you can see that the graph is going towards infinity, so it will never touch this point. But again, these points will hence not be in the domain of tangent of x. But as you can see, the y values, they go from infinity to negative infinity, so all real numbers, the range. And another way of basically explaining the tangent function is by breaking it down into sine and cosine functions, right? So you can write down tan of x like this. It's basically tangent of x is equal to the sine of x over the cosine of x. So at any point where cosine of x is equal to 0, this function becomes undefined, so it will not be in the domain. So cosine of x must not be equal to 0. And at all odd multiples of pi by 2, cosine of x is equal to 0. Hence, it is not in the domain. Similarly, you have cotangent of x, which is basically just the reciprocal, so it is 1 over tangent of x, right? So cotangent of x is equal to 1 over tangent of x, and that will be equal to cosine of x over the sine of x. And as you know, sine of x here must not be equal to 0, and at every single multiple of pi, sine of x is equal to 0. Hence, it is not in the domain of this function. But again, the range is all real numbers. And again, you have secant of x, which is basically secant of x is equal to 1 over cosine of x. And in this case, again, as we did in the case of tangent of x, cosine of x must not be equal to 0. Hence, it will have the same domain and range as the tangent of x, right? So you can see this, and it has the same range as well. And you have cosecant of x, which is the reciprocal, of the sine function. So basically, cosecant of x is equal to 1 over sine x, which means that it will have the same domain and range as the cotangent function, because sine x is in the denominator, right? So hence you have all real numbers except for the multiples of pi, right? But you have a difference in the range as well. Once you plot the graph of cosecant of x, you'll understand that the range is this. The absolute value of y must be greater than 1, right? So that's what this is. Now we need to discuss inverse trigonometric functions and exponential functions. Again, once you plot the graphs, you'll understand. But in simple terms, when y is equal to sine inverse of x, you take sine to the left-hand side, and then it will take the sine inverse function to the other side, and it will become a sine function. So in this case, x will be equal to sine y. And once you plot the graph for this particular case, you'll find out that this is the range and this is the domain. And you have same rules for every single inverse trigonometric function. And once you plot the graphs, you'll find out the limitations in the range and the domains, right? But the simple rule of thumb is that when the inverse function is on the right-hand side, you take it to the left-hand side to make it into a normal function, a trigonometric function, basically. Now let's discuss exponential functions. A function in which the variable basically x appears as the exponent is called an exponential function. Sorry, I have a bit of a cough. Now, here's an example. You have e to the power a of x. Now you see this x over here, it's in the exponent, right? And similarly here, x is in the exponent. In this case as well, x is in the exponent. In this case as well, x is in the exponent, right? So these are all exponential functions of x. Fairly simple. Now let's define a logarithmic function and a hyperbolic function. Now, basically, a logarithmic function is another way of writing down an exponential function, right? So if you have this function here, x is equal to a to the power y, right? Where y is the input and x is the output in this particular case. But the definition says that that y is the output. So how will you write down this y as the output, right? How will you write down y as the dependent variable here? So you need to think of some way, and that way is through a logarithmic function. So you can write down x is equal to a to the power y like this, where the exponent becomes the dependent variable, and that will be equal to the log with the base a, which is the constant here, into log with the base a of the independent function, which is x, right? So just another way of writing down x is equal to a to the power y is equal to the logarithm with base a of x. And you don't need to worry about what this basically is, because you have this particular function in your calculators. So you can just simply calculate this, right? Now, a must be greater than 0 and a must not be equal to 1. Those are the only two conditions here, right? So if they are, then, well, tough luck, honestly, because if a is equal to 0, in that case, you'll just get 0 on this side, because 0 to the power anything is just 0. So both sides will become 0. And when a is equal to 1, again, that's just 1 to the power of something, and again, that just becomes 1. 1 to the power of a million is equal to 1, right? So fulfill these two conditions, and that is what you call a logarithmic function of x. If a is equal to 10, then we have a log with the base 10, and that can be written down as just log of x. Instead of writing down log with the base 10 of x, write down log x. That's the same thing. You have this in your calculator as well. It is known as the common logarithm of x. Now there's another one. If a is equal to e is a certain value. I don't really remember what the value is in digits, but it's a value, and you have this in your calculator as well. So when a is equal to e, you can get log with the base e of x, and that is the natural logarithm of x. And you can write down, instead of writing down log with the base e of x, just write down ln x, ln being the natural logarithm. Now, hyperbolic functions. I won't really go into too much detail here, but sine hyperbolic of x. What is the sine hyperbolic of x function? That's basically e to the power x minus e to the power negative x over 2. That's just what it is, honestly. It's just something you'll have to memorize, or it'll be given to you, but you just have to remember. This is known as the hyperbolic sine function. Its domain and range are the set of all real numbers, right? So this is the beauty of this particular function, is that the domain and range are a set of all real numbers. Now you have cos hyperbolic of x. The only difference between sine hyperbolic of x and cos hyperbolic of x is this sign between the two exponential functions, right? So in the sine hyperbolic of x, you get a negative sign, and in the cos hyperbolic of x, you get a positive sign. This is called the hyperbolic cosine function, and its domain is the set of all real numbers, but the range is a bit different. So basically, the y value ranges from 1 till infinity. So basically, y is greater than or equal to 1. That's the range, okay? And the remaining 4 hyperbolic functions are defined in terms of hyperbolic sine and this hyperbolic cosine function. So basically, for example, tan hyperbolic of x is basically just equal to sine hyperbolic of x over cosine hyperbolic of x, just like you had it in the trigonometric functions, right? And here's what it is. Once you simplify it down, you get this. And again, cotangent hyperbolic of x is just the reciprocal of tan hyperbolic of x. So you just flip down, take the reciprocal, right? So you have this, and then you have secant hyperbolic of x, which is just the reciprocal of the cosine hyperbolic of x. And then you get this. And cosecant hyperbolic of x is just the reciprocal of sine hyperbolic of x, and you get this. Simple, really. You can see that the hyperbolic functions have the same properties that resemble to those of the trigonometric functions. I think we've established that fairly well over here, right? Now, this will be a fairly short video. We'll discuss what an inverse hyperbolic function is, but you don't really need to know this at this level, honestly, unless you're from some country that really teaches advanced stuff at a very low level. I don't know, but let's see. Basically, the inverse hyperbolic functions are expressed in terms of natural logarithms, right? So basically, ln, like we discussed earlier, ln being ln x, the natural logarithm of x is basically the logarithm base e of x, right? So the inverse hyperbolic functions are expressed in natural logarithms, and again, like I just said earlier, we shall just study them in higher classes, honestly. But just a brief overview of what it is. Here, you have sine hyperbolic inverse of x. That is the natural logarithm of x plus under root x squared plus 1, right? And the domain of this function is all real numbers, right? Now, cos hyperbolic inverse of x, the difference, again, as you remember, in the normal hyperbolic functions, the difference between the sine hyperbolic function and the cos hyperbolic function was just a single addition and subtraction sign. Similarly here, you have this positive sign in the sine hyperbolic inverse function and this negative sign in the cos hyperbolic inverse function. And otherwise, it's the same. But because of this negative sign here, there is a condition that says that x must be greater than or equal to 1. And the only reason for that is because it cannot have a negative number under this under root sign, right? Because you cannot take the under root of a negative sign, because that will become an imaginary number, and we're not dealing with those, honestly. So yeah, that's why the domain is all numbers, all real numbers greater than or equal to 1. Now, tan hyperbolic inverse of x, as you might have guessed by now, it just is something like this, right? And basically, you'll have to memorize a lot of this stuff. But let's talk about the domain of this particular case. Now, the domain states that you can, for a natural logarithm, you must have a certain value here, and that value must never be basically equal to 0. It must always be greater than 0, which is why you see this denominator here. The first thing is that the denominator must not be equal to 0, right? And that will be equal to 0 if this x is equal to 1. So we've got that cleared out. But this entire thing must not be equal to 1 either, because as we discussed earlier, that for the logarithmic functions, the value of x, the value of basically this function inside the logarithm, let's not say x, let's say that if you have ln of, say, a, and a is a function, a is an input variable, the condition here is that a must be greater than 0 and a must not be equal to 1. And over here, you must fulfill that condition on this entire term, 1 plus x over 1 minus x. And these two conditions can only be fulfilled if the absolute value of x is less than 1. So basically, this states that x must be greater than negative 1 and must be less than 1. Okay? So, yeah. This is basically the 3 inverse hyperbolic functions. And you have these 3 as well, which are basically the reciprocals of the previous ones. Cotangent hyperbolic inverse of x is, again, the reciprocal of the tangent hyperbolic inverse function. And again, you'll just have to memorize a lot of this stuff. Secant hyperbolic inverse of x is like this, and the cosecant hyperbolic inverse of x is like this. And these calculations are a bit too tricky. But again, remember that the conditions in the function inside of the natural logarithm, you must fulfill the conditions to get the domain. And in this case, it's the absolute value of x is less than 1. In this case, the secant hyperbolic inverse of x, this is the domain, x is greater than 0 and less than or equal to 1. And in this case, the cosecant hyperbolic inverse of x must not be equal to 0. Simple. Okay? And you can verify this by actually plugging them in here, because let's take cosecant hyperbolic inverse of x. If you plug in x is equal to 0, this term becomes 0, and hence you just know that it becomes undefined. And over here as well, see, you have this x absolute in the denominator, so this becomes undefined as well. Other than that, if you plug in any number over here, in this case it's x squared, so any negative number of x will become positive as well. So you can take the under root, and eventually you can calculate the natural logarithm, right? So verify all of these and you get it. Now let's discuss explicit functions and implicit functions. So if y being the dependent variable, sorry, sometimes the pen acts a bit weirdly, but y being the dependent variable here, if y is easily expressed in terms of the independent variable x, then y is called the explicit function of x. Like here, see this example here? The y variable is clearly expressed in terms of the independent variable as a function of the independent variable x, right? This is the function of the independent variable x, and it is completely separated from the dependent variable y, right? So honestly, that makes things quite easy for everyone. Explicit functions are just beautiful. That like just make things a lot easier, and in many cases you'll have to convert a function into this form, right? So for example, if you had, say, a function, and let's say that's 2xy plus 4y is equal to 1. This right now looks a bit weird, but this is, in this case, y is an explicit function of x as well, because you can just take y common here, right? 2x plus 4 is equal to 1, and then take this to the denominator, in which case it becomes y is equal to 1 over 2x plus 4. Oops, sorry, 4, right? And look at this example here. Again, y is clearly separated from the independent of variable x, and so this is also an explicit function of x. And symbolically, it can be written down like this, right? Like I said, y expressed as a function of x. Now, an implicit function makes things a bit more difficult, honestly. So if x and y are so mixed up that y cannot be expressed in terms of the independent variable x, basically you cannot write y clearly as a function of x, then y is called an implicit function of x, right? See this example here. Are you able to separate y from this? Because look at this. At the max, what can you do? You'll first of all take this x square to the right hand side, okay? So that becomes xy plus y square is equal to 2 minus x square. Fine, but what will you do now? If you take y common on this left hand side, you'll still be left with an extra y term here in the y square term, right? So at the max, what can you do? You can just take one y common here. That'll become x plus y is equal to 2 minus x squared. Now both this term has a y and this term also has a y. So you cannot take this x term here separately, and hence you're stuck. And this is an implicit function of x. Same is the case here. You'll try very hard, but you cannot separate y from x completely on one side of the equation. So these two are implicit functions of x and y. And since they cannot be represented like this, this is how you will represent it. Symbolically, you write it down as a function of x and y. and that will be equal to something. So this is an implicit function of x. Now let's see what parametric functions are. Now, one thing you must remember here is that as your education advances, things become a bit more confusing, and this is one of those things. But it's not really confusing at all, honestly, once you learn what it is. Sometimes a curve is described by expressing both x and y as a function of a third variable, which can be anything, but in general we have t or theta, t being time and theta being an angle. So basically x and y change with respect to time or with respect to theta, the angle. And these two are called parameters. And the equation is of this type. Basically x is a function of time and y is also a function of time. And these are called the parametric equations of the curve. So both x and y are defined by a third variable, which is common to both x and y. In this case, it's time. So here's an example. X is equal to a into t square. So x here acts as the dependent variable and t is the independent variable, and x is now a function of t. So basically x is equal to a function of t, which is equal to a t square, right? Similarly here y is equal to a into t. So y is also a function of t, right? Now here's another example. X is equal to a into cosine of t. So x again is a function of t. Y is equal to a sine of t. So y is also a function of t. And as you progress further and further in your education, you will encounter a lot of this, a lot. So be very clear about what it is. You'll not be able to see this t clearly because if you have an xy plane, the t is not there. So you must be careful. And remember that x and y in the cases are functions of a third variable that you're not seeing in front of you. Here you have x as a function of an angle, which is theta, and y is also a function of an angle theta. So they change with respect to the angle. So the value in here, well, again, the value of x changes with the value in theta, as x is a function of the angle theta. Same is the case for y. I hope that clears up what a parametric function is. Let's discuss even and odd functions. Now, you know about even and odd numbers, but how can a function be even or odd? Well, let's see. An even function is a function f if it is even if f of negative x is equal to f of positive x. So for example, any function, if it yields the same result for f of, say, negative 2 and and f of positive 2, or any number, then it's an even function. So let's say you have this function here, right? So you take this function, f of x is equal to x squared. Now, if you plug in f of negative 2, that will become negative 2 whole square, right? Because x is replaced with negative 2. That is equal to 4. So if you plug in positive 2 here, that will become 2 whole square, which is also equal to 4. And this is true for any real number. If you plug in negative 100, and if you plug in a positive 100, it will give you the same result, which is basically 10,000, right? So in any function where if you plug in a negative number and you plug in the positive number of that as well, and it yields the same result, That's an even function. Another very nice example of this is the cosine function. Now see here, the cosine function, the graph of the cosine function looks something like this. It looks like this. Now, if you plug in, say, f of negative pi by 2, that's this point here, right? This is pi by 2. And as you can see, the y value over here is 0, right? And so this becomes 0. Now, what if you plug in positive pi by 2? Well, that's this part here. This is negative pi by 2 and this is positive pi by 2. And this also yields 0. So this is true for any number x in the entire plane for this function cosine of x. And this is a very important lesson you'll learn. You see this y-axis? If the graph of a function is symmetric through the y-axis, that function is always an even function, right? So if you had, say, this function here, I don't know what to call it, but let's say you have a function that looks like something like this, and it has a similar, I'm not really that good at drawing, but let's say it looks like this, right? You can see it's almost, my drawing is not that good, but let's assume it's symmetrical. Let's say that the y-axis acts as a mirror. This side and this side both are symmetrical. This is also a even function. So that covers an even function. Let's see what an odd function is. If f of negative x yields negative f of positive x, and that is true for every number x in the domain of f, that function is an odd function, right? So here is an example. If f of x is equal to x cubed, let's take this one. Now, if you plug in, as you know that the domain of x cubed is any real number, so let's just take an example, f of, say, negative 2. What's that equal to? That's equal to negative 2 to the power 3, and that is equal to negative 8. What if you plug in f of positive 2 and you plug in a negative sign before it? Well, that becomes negative 2 to the power 3. That's equal to negative 8 as well. And this remains true for the entire domain for any real number. Hence, f of x is equal to x cubed is an odd function. And let's take another weird example. This one, sine of x, it's also an odd function. Why is that? Well, let's draw the graph for a better explanation. The sine graph looks something like this. Right? And it goes on from negative infinity. Let's just, right? Now look over here. If you plug in pi by 2, sine of negative pi by 2, that is this part here, that yields a result of negative 1, right? This is negative pi by 2. That gives you negative 1. So that should be equal to minus sine of positive pi by 2. So put this negative sign here, and what is sine of positive pi by 2? Well, positive pi by 2 is here. And that yields a result of 1. So that becomes negative, which is the negative from this sign here. And sine pi by 2 is equal to 1. So 1. So that is equal to negative 1. This and this are equal, and that fulfills the condition of an odd function. This remains true for the entirety of the domain of sine x, which is all real numbers. You can test this out if you want. So I hope that clears up what an odd function and an even function is. Now let's find the value of a function at a given point. So we have this question here. It says that the function of x, f of x, is equal to x squared minus x. And now we have to find the value of the function of x when x is equal to minus 2. Basically, in place of this x over here, if you put on any number, that basically means that x is equal to that number, which in this case is minus 2. Now, what you simply, and we have basically three parts. We have function when x is equal to 0, and the function of x when x is equal to another function of x, right? Because x minus 1 is also a function of x. Now, let's see what we'll do in the first case. So, and this one as well. This also says that we have another function of x squared minus x squared plus 4 in the original function of x. Let's just do this step by step to understand. So let's find when the function of f, the function of x when x is equal to minus 2, right? So that just basically means that in the original function that is given to us, which is this x squared minus x, you have to replace every x with the value in the bracket. So minus 2. So that will become minus 2 whole square minus 2, right? And so that just gives you 4 plus 2, because this negative and this negative are multipliers, so it will become a plus sign, and that gives you 6. Fairly easy. And the next one is fairly easy as well, because the function was, again, let me just write that down again. F of x is equal to, f of x is equal to x squared minus x. And since x is equal to 0, so this will become 0 squared minus 0, right? Fairly simple. That gives you 0. Now, here's another one. F of x minus 1. And like I said earlier, the simple way to solve this is to replace this x and this x with whatever is in the bracket, and that is x minus 1, right? So this becomes x minus 1 whole square, and this becomes just x minus 1. So this becomes x minus 1 whole square, and this becomes x minus 1. And you'll have a negative sign between them, right? So yeah, this is what you get. And when you add that all up, you have to first solve this quadratic expression and this linear expression, and eventually you end up with the quadratic expression, right? So just remember that, for example, if it said that in this particular example, let's say they asked you that f of x is equal to x squared minus x, and then they said that g of x is equal to x minus 1, and then they told you to find f of g of x. That just basically means that, right, that just basically means that f of whatever g of x is, and that is x minus 1, right? So they can ask you the question like this as well, and that'll just, you have to do the same thing. Okay, similarly, you have this example over here, right? Again, remember the original function, f of x is equal to x squared minus x. So in place of every x, just replace it with x squared plus 4. And that just basically gives you this, x squared plus 4 whole square. That'll give you an equation to the power 4 with a degree of 4. And this is just the original expression in the brackets, right? So that eventually gives you this, right? So this is a very, very simple process to find a value of a function at a given point, right? Now let's evaluate a function, right? It says that we have to find this entire expression and we have to simplify it at the end. So it says that f of x is equal to 6x minus 9, right? So once we have f of x, and now we have to find f of a plus h, right? So what that basically means is that in every, right, if you remember again, that the way to solve a function is that you see what's in this bracket, a plus h, replace that with every x. So this x here becomes a plus h, right? So instead of 6x, you have 6 into a plus h, right? And 9 is a constant, so obviously it's not multiplied with anything. So we have to find this one separately, and we have just h. H is a constant, so it just be written down as h in the end. So basically we have to find these two functions, and we've been given the actual function itself that we have to do in respect to. So f of a plus h is equal to 6 into a plus h minus 9, right? Now we have to find f of a. So that just basically means instead of x, you write down a, right? So f of, and again, you just simplify the whole expression that comes up to this. Now let's just find f of a. F of a is equal to 6a minus 9 because f of x is equal to 6x minus 9. So obviously f of a will be 6a minus 9. Now that you have the two expressions, you can just simplify the whole thing that we had to find originally, right? So what that basically means is that since f of a plus h is equal to 6a plus 6h minus 9, you just write down this becomes basically 6a plus 6h minus 9. Put that in a bracket. This negative sign here, write that down. And then in the bracket, write down f of a, which is 6a minus 9. 6a minus 9. Do not forget these brackets again. And divide that entire thing by h, right? Now, again, that's the same thing you have over here. And now you have to simplify it. So, just close, do this, multiply this negative sign with 6a minus 9. You get minus 6a plus 9. And just do all the subtraction. This will be subtracted with this, so cancel them out. And this will be subtracted with this, so cancel them out. So you're just left with 6h over h. And further simplification just leaves you with, since h and h get cancelled out, you're left with 6. And so this is how you evaluate this entire expression when the original function is given to you. Now let's express the perimeter of a square as a function of its area. Now, this is a question that is asked a lot in, to be honest, most exams. Like in most entrance examinations and even in the SAT and the ACT, this is a very common question because, well, it's just everybody is familiar with the perimeter of a circle, perimeter of a square. It's just the total length of the sides of the square. So if you have this square, right, it just means that you have to add up the total length of the border, right? Now, the perimeter, let's call it P, of a square as a function of its area A. So the area is A, and we have to express A, we have to express P in a way that can be found by the area of the square. Now, the area of a square is a very different thing from the perimeter of a square. The area of a square is the area that it covers. So this entire thing, it is not the boundary, the length of the boundary. So let's see how you'll do that. Well, we'll let the length of the square be equal to x, right? Because since since the square has all equal sides, that means this side is equal to x, this side is equal to x, and this side is equal to x, and this side is equal to x, right? So that's the length of the square. And obviously, again, since the length of the square is x, the width of the square is also x because all sides are equal. Right, now I have this square over here. The perimeter of a square is equal to all the sides added up. right? The total length. So that is equal to 4x. Now this is given to you. Not given to you, well, you just know that it is what it is, 4x. Now, we have to find this in a way that it can be found out by the area of the square. We need to find an expression that expresses p in the as a function of the area a, right? So now that we know that the parameter is equal to 4x, we need to see what the area is equal to. The area of a square can just be found by multiplying the length with the width, and both are x, so that just becomes x square, right? So x is equal to under root a, right? Now that one length is equal to the under root of the entire area, that just simplifies it a lot, right? We need to put x is equal to a in the equation where it said that p is equal to 4x, right? Now you replace this x over here with under root a, and that gives you 4 into under root a. And now you can see that p is expressed as a function of a, right? Now if they asked you to find the area of the square as a function of the parameter, what do? Well, that just becomes, you just have to isolate a and take everything to the side of p. So that just basically means that you take this 4 to the left hand side, and that becomes p by 4 is equal to under root a, and so a becomes p square, because you'll have to square this entire side, this left hand side, so that gives you p square over 4 square, which is 16. So now you have area as a function of the parameter, right? So yeah, let me just write that down. Area as a function of the parameter. Well, let's find the unknowns in the function where we have its domain given to us. This is the function, right? The unknowns are a and b. Now, let's see what is given to us. It says that the function f of 2, so this x becomes 2 in this case, the function of 2 is equal to minus 3, and the f of minus 1 is equal to 0. You've been given two domains, the value of the function at two domains. One is minus 3 when the domain is 2, and one is 0 when the domain is negative 1. We have to find a and b, right? So let's see. Well, first of all, let's see what happens when we plug in x is equal to 2 in this function, right? So f of 2 is equal to 2 cubed, because this x is replaced with a 2. This x is also replaced with a 2, so that becomes, instead of a into x squared, that becomes a into 2 squared. This x is also replaced with negative 2, so instead of b into x, that becomes b into 2. This one is a constant, so it remains as it is, so that is just left as it is. Now, once you evaluate this, you get 9 minus 4a plus 2b. So f of 2 is equal to 9 minus 4a plus 2b. Now let's see what happens when you find f of negative 1. Plug in x is equal to negative 1 in the function now. So instead of x cubed, well, remember the original function, that was f of x is equal to x cubed minus ax squared plus bx plus 1. So instead of x cubed, you have negative 1 cubed. Instead of ax squared, you have a into negative 1 squared. Instead of bx, you have b into negative 1. And this constant is as it is. So f of negative 1 gives you minus a minus b. Now, remember, let's look at f of 2 first. We found f of 2 earlier, right? That was equal to 9 minus 4a plus 2b. And the actual end value of f of 2 is equal to minus 3. That was given to us in the original question. So 9 minus 4a plus 2b is equal to negative 3. So Once you simplify this, well, just take this 9 to the right hand side. So minus 3 minus 9 on the right hand side and minus 4a plus 2b on the left hand side. Minus 3 minus 9 gives you minus 12, and take 2 common on the left hand side. So that becomes minus 2 into 2a minus b. Fairly simple. Take this negative 2 to the right hand side. So negative 12 divided by negative 2. That gives you 6. So 2a minus b is equal to 6. Now let's do the same procedure for f of negative 1. F of negative 1 gave you minus a minus b, and f of negative 1 is equal to 0, as is in the original question. So equate minus a minus b equal to 0. So minus a is equal to b, and now multiply both sides with negative 1. Right? And so a is equal to negative b. Now plug in this value of a, which is equal to negative b, in place of this a, right? And so you get 2 into negative b minus b is equal to 6. So minus 2b minus b is equal to 6. So minus 3b is equal to 6. Take this negative 3 to the right hand side and divide it. So 6 over negative 3 is equal to negative 2. Now that you have this value of b, put it into the equation that we found earlier, which said that a is equal to negative b, right? So instead of this b, plug in negative 2. So a is equal to minus negative 2. And that gives you a is equal to 2. So we've now found the value of b, which is negative 2, and the value of a, which is 2. Right? So we've now found the two unknowns. If in the original question it had a third unknown, c, you'd need 3 values of f at 3 different domains, right? And so on and so forth. Let's show a parametric equation represents a parabola. We've discussed what parametric equations are, right? They're basically just two functions that have they're two functions of a common variable. So let's see an example. It says that x is equal to at squared. What that basically means is that x is a function of t, right? So in this case, f of f1 of t, the first function of t, is equal to at squared. And the second, y is equal to 2at. So f2 of t is equal to 2at, right? And it represents the equation of a parabola, which is basically y squared is equal to 4ax. We need to show that these two parametric equations of x and y are equal to the equation of the parabola, right? So let me just rub this off for now. I just need to show you how they were functions of a common variable t. Now let's see. This is given to us and this is given to us, right? So let's see. We need to isolate t over here in this second equation, right? So take this 2a to the left hand side, so it becomes y over 2a. T is equal to y over 2a, right? Now that you have this value of t, replace it in this function, in this equation over here, right? So this t square over here becomes y over 2a. So x into at squared becomes now x is equal to a into y over 2a whole square. Now further simplify it, and basically now just cancel out this a with one of the a's over here, right? So just this 2 becomes 1, so that becomes y squared over 4a. And now you take this 4a to the left hand side and multiply it with x. So y squared is equal to 4ax. We've proven that y squared is equal to 4ax, and that is the equation of the parabola. Now let's see what the composition of functions are. Let's say that f is a function from set x to set y. So f of x is equal to y, right? And let g be a function from set y to set z, which means that g of y is equal to z. Now, since y is equal to f of x, it's fair to assume that we can write down this y as f of x. So g of f of x is equal to z, right? The composition of f and g is a function denoted by g of, right? We need to express this g in another way, and that is g of from set x to set z. So g of x is equal to g of f of x, right? So instead of writing this g of f of x is equal to z, you can just write g of x. So let's see the explanation. Let's consider two real valued functions of f and g, right? F of x is equal to 2x plus 3. G of x is equal to x squared, right? Now that we have this, then g of x is g of f of x, right? As I told you before, g of x is equal to g of f of x, which means that in this f of x now can be replaced with 2x plus 3. So g of x basically means g of f of x. So that means that this x is replaced with whatever f of x is, and that is 2x plus 3. So that just basically means g of 2x plus 3, right? And what does that equal? Since g of x is equal to x squared, this x is replaced with 2x plus 3, which is now, so x squared is now equal to 2x plus 3 whole square. Let's see what the inverse of a function is by the arrow diagram. So we'll let f be a one-on-one function from x onto y. So f of x, oops, just a second. So f of x is equal to y, right? The inverse of f is denoted by f inverse. It is a function from y onto x. Now it's the opposite way. So basically what that means is that f of, when you take this f to the right hand side, so f inverse of y is equal to x. F of x is equal to y, so f inverse of y is equal to x, right? X is equal to f inverse y. If and only if y is equal to f of x, right? That's just given, really. Now, and another thing, again, one-on-one function. That's necessary to remember. See, this is the diagram. F basically maps this x onto the set y, right? The terms in this set x onto the specific terms in y, right? So the opposite way around, when you need to map basically this y onto this set x, so values of y that will give you values of x, that is where you use f inverse, right? So basically the y set has the range of the function f, but it has the domain of the inverse function f inverse, right? But it is the opposite way around for this. In the case of the set x, the domain is of the function, but the range is of the inverse function, right? It says f inverse of y is equal to x, right? So the inverse function reverses the correspondence of the original function. That is what I told you earlier. F of x is equal to y, so f inverse of y is equal to x. Another very good example of this is that the sine function, right? You know that sine of x is equal to y. If sine of x is equal to y, you know very well that when you need to find x, you take sine inverse of y. That'll give you the value of x at that y point, right? So f inverse y is equal to x when f of x is equal to y. That's just simple. Now, let's have a question. Let's say that we have to find the inverse of a given function. We need to find f inverse of x when f of x is equal to minus 2x plus 8, right? Now, we know that y is equal to f of x, right? This f of x is equal to y. So x is equal to f inverse y, right? As we discussed earlier. Now, f of x is equal to minus 2x plus 8, which means that y is equal to minus 2x plus 8, right? But we need to find f inverse of y. So let's separate. F inverse of y is equal to x. So we need to separate the x over here in this equation to find f inverse of y. So you isolate x. First you take this 8 to the left hand side. So it becomes 8 minus y, and that is equal to 2x, right? You take this, actually not take this 8 to the left hand side, you take this 2x to the left hand side and take this y to the right hand side. So 2x is equal to 8 minus y, and then you take this 2 to the right hand side. So 8 minus y is now divided by 2. So now x is equal to 8 minus y divided by 2. So now, since x is equal to f inverse of y, replace this x with f inverse of y. So f inverse of y is equal to 8 minus y over 2, right? So simply what f inverse of x is, you just replace this y with x, like you did earlier for normal functions. Since f inverse of y is equal to this, now in every place where you have a y, which is just this case over here, you replace it with x. So f inverse of x is equal to 8 minus x over 2 instead of 8 minus y over 2. So that's how you find the inverse of a function. Now let's see the composition between a function and its inverse. It says that we have to basically find f inverse of minus 1 first, and f of x is given to us. So first we need to find f inverse of x and then input minus 1. And then we have to verify that f of f inverse of x and f inverse of f of x is equal to x. Okay? Now, we did this before, but just to recap that, to find the inverse of f of x, first you write down f of x because f of x is equal to y as well. So you write down y is equal to minus 2x plus 8. And then basically you isolate x. So once you isolate x on the left hand side, you get x is equal to 8y minus 8 minus y over 2. Okay? And then you basically, this x here is basically f inverse of y, right? Because if y is equal to f of x, then f inverse of x is equal to f inverse of y is equal to x, right? So this x can be equated to f inverse of y. So f inverse of y is equal to 8 minus y by 2. But we have to find f inverse of x. So instead of y, you input x. So now this y is replaced with x. Okay, so now that you have f inverse of x, you can find f inverse of minus 1 by inputting minus 1 in place of this x. Right? So you input x is equal to minus 1 over here. Once you do that, you get 9 by 2. So f inverse of minus 1 is equal to 9 by 2. Now, what did we have to find? We had to prove that f of f inverse of x is equal to f inverse of f of x, which is equal to x, right? So first let's prove that f of f inverse of x is equal to x, and then we'll prove f inverse of f of x after this. Okay, so if you input f of f inverse of x, you get f of 8 minus x by 2, right? Because f inverse of x was equal to 8 minus x by 2. So now you have to input 8 minus x by 2 in the original f of x function. And what was that equal to? If you remember, f of x was equal to minus 2x plus 8. So instead of this x now, you get f inverse of x. So now you have minus 2 into 8 minus x by 2 plus 8. So that equates to x, right? Because you can cancel out this 2 and this 2, and then multiply this minus sign with 8 minus x, so you get minus 8 plus x, and then you can cancel out this minus 8 and this plus 8, so you get x. Now, the other part. We need to prove that this f inverse of f of x is also equal to x, right? So, what was f inverse of x? F inverse of x was equal to 8 minus x by 2. So f inverse of f of x is equal to f inverse of minus 2x plus 8, because f of x is equal to minus 2x plus 8. So now in place of this x over here, you input minus 2x plus 8, right? So once you multiply this negative sign with this entire bracket, you get 8 plus 2x minus 8. You can cancel out this positive 8 and this negative 8. That gives you 2x over 2. You can cancel out this 2 and this 2, and that leaves you with x. So now you've proven that f of f inverse of x is equal to x, and f inverse of f of x is also equal to x. Now let's see what the limit of a function is. So it says that if we let a function f of x be defined in an open interval, what that basically means is that the domain of x is basically an open interval, and let's say that it's from, say, it includes 0 and it goes to a, right? But it does not include a itself. It is less than a, right? So let's just say that it is defined in this open interval near the number a. If as x approaches a from both the left and the right side of a, f of x approaches a specific number L, which is the limit of f of x as x approaches a, right? And this is how it is written, but let me just first explain what this basically means. It basically means that, for example, if you have this graph here, right? And let's say that you have this particular shape over here, right? So if we take this point here, right? Let's say that it exists as x is equal to 3, right? Now, you can see that if you look at the left-hand side of this point, the graph approaches this point, right? Then you look at the right-hand side of the graph. You can see that the graph approaches this point from the right-hand side as well. Since the graph approaches this particular point from both sides, this side of x and this side of x as well, the left and the right-hand side, and it approaches the same point, 3, that means that the y point, the y coordinate of this point is the limit, right? So basically what this is it is located at 3 and at L. Okay, so this is how it's written. X the limit of f of x as x approaches a is equal to L, right? So basically, if you look at this particular example here, let's say that the y point over here is equal to 4. So what you write this particular example down as is limit as x approaches 3 is equal to 4. Okay, so this is just the basic explanation. You might be thinking that right now every graph is like this, but no, some graphs do not exhibit this particular property, right? So we'll see that later on. Let's see the theorems on the limits of function. We have 6 theorems in total, and let's just get right into it. So first we assume that we have two functions f and g, and the limit of f of x as x approaches a is equal to L, but the limit of g of x as x approaches a is equal to m, right? So both of these functions have different y values for when x approaches a, right? So they can basically just say it's like this. Say this is one graph and this is the other graph. So obviously you can see that if we say that this here is a, the limit over here is different and the limit over here is different. So two different functions. Okay, so let's see the first theorem. The first theorem states that if we can basically write down the limit of x approaches a of f of x plus the limit of g of x as x approaches a. You can write that down like this as well. You can take the limit common from both of them, and it will be the same thing. It will become L plus m. Okay, so the first theorem states that you can take the limit common if they both have the same limit. Okay, if they're both being added up, you can take the limit common. The second theorem states that the limit of the difference of two functions is equal to the difference of their limit. So it basically means the same thing. In case of both addition and subtraction, you can take the limit common from both of them, and that in this case is equal to L minus m, because limit of f of x as x approaches a minus limit of g of x is equal, the limit of f of x as x approaches a is L, and limit of g of x as x approaches is m with a negative sign between them, right? But you can take the limit common. Okay. The third theorem states that if k is any constant, then basically if we have the limit of k of f of x as x approaches a, it is basically equivalent to as if you take the k outside and you multiply k with the limit of f of x as x approaches a, which is equal to L. So that becomes KL, right? The fourth theorem states that the limit of the product of the functions is equal to the product of their limits. What that means is this. Basically, the limit of the product of f of x and g of x as x approaches a is equal to the limit of f of x as x approaches a multiplied by the limit of g of x as x approaches a, right? So in this case as well, you can take the two limits common outside as 1 and multiply the two functions, and that just becomes L into m, right? The fifth theorem states that the limit of the quotient of the functions is equal to the quotient of their limits, provided that the limit of the denominator is non-zero. See here, basically the limit of f of x over g of x as x approaches a is equal to as if you just divide the limit of f of x divided by the limit of g of x. But you have to remember that this term here cannot be 0 for this particular theorem, right? Because that becomes, once you have a 0 in the denominator, the term itself becomes uh, it does not have any value. It becomes infinity. It gives you a math error. So as long as this is not, the denominator is not equal to 0, this entire thing over here is equal to L by M, right? So you can take these two limits common outside as 1 and then just divide the two functions. Okay, so now the limit of f of x whole to the power n, where n is an integer, basically means that if you have the limit of f of x whole to the power n with as x approaches a, you can basically take it as the limit of f of x as x approaches a whole to the power n. So that becomes L to the power n, right? So these are the 6 theorems, and you can use them to your luxury. The only thing that you have to remember here is this particular case, right? Over here, this g of x and this m over here, they cannot be equal to 0 because this whole thing becomes undefined. Now let's use the binomial theorem to prove an important result. It says that we have to prove that 1 plus 1 by n whole to the power n as, this is not x, this is n, as n approaches infinity is equal to e, which is a constant in mathematics, which results in something like 2 point something something. It's in your calculator, you can find out the exact value, but we have to prove this. So first we'll apply the binomial theorem on this 1 plus 1 by n to the power n. When you apply the binomial theorem, you get this 1 plus n into 1 by n plus n into n minus 1 by 2 factorial into 1 by n to the power 2, and so forth. You basically just keep on multiplying the numerator over here with n minus 2 in the third term, n minus 3 in the fourth term, n minus 4 in the fifth term, and so forth. And in the denominator, you basically just take factorials of numbers consecutively. So for example, in the third term over here, you get 2 factorial, in the fourth term, you get 3 factorial, in the fifth term, you get the fourth factorial, and so forth. And basically, the term 1 by n, you take powers of n minus 1 as well. So the power of 2 in the third term, the power of 3 in the fourth term, and so forth and so forth. We've discussed binomial theorem before, and if you need to refer, you need to find out what the binomial theorem is about, you refer to that lecture. Okay, but for right now, we've expanded this term binomially, right? Now, when you take some terms common, it will help, because this n and this n are cancelled out and you're left with 1 over here as well. Okay, and you can write this term down as 1 over 2 factorial. So you can take this one over here and this 2 factorial over here outside, and you can then just basically multiply this. So basically now you have n into n minus 1 over n, and when you basically just expand this further, you get 1 minus 1 by n, right? And when you do these simplifications on and on for the fourth term, the fifth term, and sixth term, you basically just get more terms that are like this. Okay, so for example, the next term after this term over here would be 1 by 4 factorial into 1 minus 1 by n into 1 minus 2 by n into 1 minus 3 by n, right? So for example, the next term that let me just write it down for simplicity's sake, right? Into 1 minus 1 by n into 1 minus 2 by n into 1 minus 3 by n, right? This is, and so forth, right? You get the gist. Now, when you apply the limit as n approaches infinity on the 1 by n terms or the 2 by n terms, like this term over here and this term over here, this term over here, any term with n in the denominator, right? They all tend to 0 because anything divided by infinity becomes 0, right? So all these terms become 0 and you're eventually left with this, right? And when you add up all these terms, as you can see, the number is becoming smaller and smaller because the denominators are getting larger and larger, right? So we will approximate this, and what this approximates to is E, which is 2.718281, so forth and so forth. So the approximate value of this is E, and that's how we've proven that 1 plus 1 by n to the power n as n approaches infinity is equal to E. Now let's find the limit of a logarithmic function. It says that we have to prove that a to the power x minus 1 over x with x approaching 0 is equal to the natural log of a. Okay, so the first thing that you have to do is that you have to substitute the numerator with a random variable, let's call it y. Okay, so a to the power x minus 1 is equal to y. Now we need to separate x. Once you isolate x, x turns out to be log base a of 1 plus y. Okay, and how you get that is basically once you get this, basically x is equal to the log base a of 1 plus y. We've done this before. Now, once you get this, you now basically have to substitute every x over here with the y term. Okay, so a to the power x over here becomes 1 plus y, for example. But now that you're writing all of this expression in terms of y, you need the limit to be in terms of y as well. So when x approaches 0, what does y approach? It approaches 0. How do you know that? Look at this, right? So when x approaches 0 over here, that means a to the power x becomes a to the power 0 minus 1. And that's just 1 minus 1, which is equal to 0, right? So as x approaches 0, y also approaches 0. Okay? Now that you have this, you can write down this term that was given in the question as this. Okay? So you replaced a to the power x minus 1 with y because that's what you did in the substitution. And you replaced the denominator x with log a of 1 plus y with the limit of y approaching 0. Now, you can take this y to the denominator, and in the denominator it becomes 1 over y because anything in the numerator becomes its reciprocal in the denominator. Okay, now that you have this, you can take this 1 over y to the power of 1 plus y over here, log a 1 plus y, because that's the rule of logarithms. Anything being multiplied with a logarithm goes to its power. Okay, now that you have this, you have to prove that it is equal to log e of a, the natural log of a. Well, you basically do that by finding another form of this, and that you can do by taking basically this entire term becomes log the natural log of 1 plus y to the power 1 over y, 1 plus y to the power 1 over y over the natural log of the base, which is a, right? And now that you have this, you can substitute it over here, right? So this becomes, this entire thing over here becomes 1, the limit as y approaches 0 is equal to log, the natural log of a over the natural log of e into 1 plus y raised to the power 1 by y. Now you'll apply the limit. Oh, this is not, it should be over here. Now you apply the limit on both the numerator and the denominator separately, because that's a theorem we've discussed. Now when you apply the limit on the numerator, it's unaffected because there is no y term in the numerator, right? It's just the natural log of a. In the denominator, when you apply it, it becomes 1, right? So eventually you're just left with the natural log of a, and that's what you had to prove. But why does the denominator become 1? Well, you remember the binomial expansion that we did earlier on in the previous lecture, the binomial expansion of limit n approaches infinity of 1 plus 1 over n to the power n, right? If you take n is equal to 1 by y, and you basically replace n over here, the n terms, with y terms, equivalent y terms, you get this. And this was equal to basically logarithm of e, which is equal to 1. And once you apply this logic, we'll discuss this earlier, this is a deduction basically, and basically this form is equal to 1 when you apply the limit. Okay, and we'll discuss it later on how we've done this, but just right now this is an explanation for why this becomes 1, and you're just left with the natural log of a. Now let's see some deductions and important results. The first deduction is this, right? Why is this equal to e? Because we know that as n approaches infinity of 1 plus 1 over n whole to the power n, that is equal to e as well. So how do we go from this to this? We substitute. We can substitute n with 1 by x, okay? So x is equal to 1 by n, right? Now substitute this and this in this. But here's the thing. Since now you're writing down n in terms of x, you'll also have to change the limit, right? So the limit must be in terms of x as well. So when n approaches infinity, right, over here, n approaches infinity, x approaches 0, right? Because 1 over infinity is 0. So now you have everything you need. This can be written down as this. This 1 by n is replaced with x, this n is replaced with 1 by x, and the limit is x approaches 0. And this new, we've discussed earlier, approaches e. Okay? Now the second deduction. The second deduction states that the limit e to the power x minus 1 over x as x approaches 0 is equal to log e of e. And that is equal to 1, because when you have a logarithm of any base of the same term as the base, you get 1. So for example, if you have log 10 of 10, that is also equal to 1, right? And the reason for that is because 10 to the power 1 is equal to 10, right? Now, we know that the limit, we know that a to the power x minus 1 over x as x approaches 0 is log e of a. We've already proven this earlier, and now we'll use the same logic over here. You can just replace this a over here with e, right? And you get this term over here, right? So now instead of log e of a, you have log e of e. Simple. You get 1. Simple. Now, here are some extra important results you should know about. the limit of e to the power x as x approaches infinity is obviously infinity, because any number to the power infinity is just infinity, right? However, e to the power x as x approaches negative infinity is 0, because e to the power negative infinity is just 1 over infinity, right? So basically, e to the power x can be written down as 1 over e to the power minus x, and as x approaches negative infinity over here, it just becomes 1 over e to the power infinity. The negative sign over here and the negative sign over here are multiplied and becomes positive infinity. So 1 over infinity is equal to 0. And this over here, as x approaches positive or negative infinity, in any case, will give you 0, right? And a is any real number, it's just a constant. So yeah. Now let's evaluate each limit by using theorems that we discussed earlier. We have to evaluate 2x plus 4 as x approaches 3, right? Now, as you know, when you have two things being added up or subtracted, you can apply the limit separately on each of them. So the 2x plus 4 as x approaches 3 can be written down as 2x as x approaches 3 plus 4 as x approaches 3, right? And you also know in the theorem that when a constant is being multiplied, right, with a variable, and the limit is being applied on the variable, you can take the constant outside, right? So the limit of 2x can be written down as 2 into x as x approaches 3. And you can just write down the constant 4 as it is, because you cannot apply the limit on it. X approaches 3 is being applied on the variable x. You have no variable over here, so 4 just becomes 4, right? Now, the limit of x as x approaches 3 is just 3, right? So 2 into 3, and that becomes 6 plus 4, which is 10, right? So this is just a very simple example. Now let's see this example over here. You have the under root of x squared plus x plus 4 as x approaches 3. Now again, the power of the under root is, well, it is equal to, basically this entire term is equal to the limit of x approaches 3, and the square root can be written down as the power 1 by 2, right? Now, this power over here, you can write the limit inside of it. You can take the limit inside the bracket and apply the power as a whole. So now you have x squared plus x plus 4 as x approaches 3 whole to the power 1 by 2, right? Now, inside this bracket, you can apply the limit separately on the x squared, the x, and the 4, right? So you have this. Now, this term over here becomes 4, because again, it's a constant. You cannot apply a limit on it. But these two, you can apply the limit on. So the x squared becomes 3 squared. The x becomes 3, and the 4 remains as it is. So this becomes 9 plus 3 plus 4 to the power 1 by 2. And that becomes 16 to the power 1 by 2, which is just under root 16. And that is equal to, well, that is equal to 4, right? And so these are just very simple problems by using the theorems of limits that we've discussed. Now let's find the limit of a function by using the formula. Now, for a real valued function, this is defined, okay? We have to find x cubed minus x over x plus 1 as x approaches negative 1. Now, the initial problem that you'll face over here is that when you input negative 1 in place of x over here, what would this become? Well, x cubed would become -1, right? And x would also become what? -1, right? And then the denominator, that becomes, x becomes -1 plus 1, and that equals 0 by 0, right? So you can solve this, but you have to convert this entire thing to a form where you can apply this limit without it being undefined, right? So you can, there's one way of solving this, that's by the L'Hopital rule, but that is not in the scope of this chapter, right? So you need to find another way, and that is by simplification. So you take x common from the numerator and you get this, right? Now, what you have to do after that is you have to apply the algebraic identity on this bracket here, x squared minus 1. You all know that a minus b into a plus b is equal to a squared minus b squared. So you can treat x squared minus 1 as x squared minus 1 squared. And that can be written down as x plus 1 into x minus 1 by this same identity, right? So that's why you have this. Now you can cancel out this x plus 1 and this x plus 1, and so you're left with this, right? And once you apply the limit of -1 over here, you get this, and this is not equal to 0. This is equal to 2, and so you found the true limit of the original function as x approaches -1. So you have to be very careful in solving questions about limits, as in many cases it will be equal to 0 over 0 or infinity or something, but in reality it isn't. You have to simplify it. Now let's find the limit by using algebraic techniques. In this case, in this particular example over here, we'll use conjugates, algebraic conjugates. So, and this is a very common technique that you'll use, like even me as an engineering major, I use this a lot. So it says that we have to find the limit of this function here as h approaches 0. Now initially when you input 0 in place of h over here, you get 0 over 0, and that is undefined. So you have to find another way to find the true limit of this function, and that's by simplifying it. But this is a very complex case over here. How do you simplify this? You can't find any typical algebraic identity to apply over here. Nothing is being cancelled out in the numerator and denominator. So what do? You multiply the numerator with its conjugate, and you divide it also by its conjugate. So basically this entire term here over here, right, this is equal to 1. So it does not affect the actual value of the function, because anything being multiplied with 1 is the same thing. But we have to convert this entire function into something that the limit can be applied upon, and this is one of those ways. You multiply the numerator and the denominator with the conjugate of the numerator, okay? So, and in some cases you have to multiply it with the conjugate of the denominator. It depends on which one it's being more complex here, right? Because this simple h over here, you cannot do anything with it, right? But the numerator is a very intricate function, this x plus h under root minus under root x, right? So you multiply the function with this the conjugate of this numerator, right? If this was in the denominator and h was in the numerator, you would still multiply it with this particular expression, because this is the more complex function. So once you multiply it, you can see that anything being multiplied with the conjugate, you can apply the property, the algebraic identity, right? So basically, if you treat x plus h over here as a, and if you treat under root x over here as b, so this is a minus b, right? And again, since this expression over here is a minus b, this expression over here is a plus b, right? And that is equal to a squared minus b squared. And that is what we've done over here, right? And the denominator is just simple multiplication, okay? Now, once you have this, you must simplify the numerator, okay? And obviously you can cancel out this under root sign with this 2. You can cancel out this under root sign with this 2 as well. And you're just left with this. And this x can be cancelled with this negative x. And eventually you're just left with this h, which will be cancelled out with the h in the denominator, right? Right. So h over h cancel out. And you're left with this. And now when you apply the limit of h approaches 0, you're left with this. This is equal to 1 over 2 into under root x, which is not equal to 0 by 0. So you found the true limit of this function by using the algebraic conjugate. Now let's solve the limit of a sine function. And that's a very straightforward way to solve this. If you have this particular example over here, and basically you have to find sine 7x over x as x approaches 0, you have to find the limit. What do you do? Well, again, if you apply the limit itself as it is over here, you get 0 over 0, because sine 0 over 0 is equal to, well, 0 over 0. And that's an undefined form. And you need to convert this into a form that will basically show the true limit as x approaches 0. And for that, you need simplification again. And the way to do that over here is basically you look at this number over here, right? And what you have to do is you have to multiply the function itself with the numerator with this number and the denominator with this number as well. So basically you're multiplying sine 7x over x with 7 by 7, right? And since this is equal to 1, it does not change the actual value of the function itself, right? But this is needed for simplification, because now over here, if you apply the limit x approaches 0, you get 1 into 7, right? And so now you can find the true limit of this function, which is 7. Now let's see the one-sided limits of a function. So far we've discussed two-sided limits, or the absolute limits, right? And basically what that means is we've discussed graphs like this, right? Say this is f of x, right? And say this here is the point C, right? And this is the limit which approaches the limit as x approaches C, right? And let's say this is L. So over here, when we say that the limit as x approaches C of f of x, which is this graph over here, is equal to L, which is true because if we approach C from both the left-hand side and the right-hand side, basically it approaches C from the left, it approaches L from the left-hand side, and it approaches the same L from the right-hand side. So we've discussed this so far, but we need to discuss one-sided limits because this is not true for every single function. And here is an example, the left-handed limit. So it says this function over here is equal to L as x approaches C from the left side, right? So basically, here's an example of how you see a left-handed limit, right? So if you have a graph that's, say, something like this, right? And at x at 0, it is basically equal to, say, L, right? Because that's here. And C over here is equal to 0. So as x approaches 0, from the left-hand side, as it approaches 0, it approaches L, right? Because this is the left hand side. But on the right hand side, there is no function at all, it's empty. So L does not exist from the right hand side. If you approach it from the right hand side, it will not approach L because there is nothing on the right hand side of the function, right? On the right hand side of 0, there is no function. So this is an example of a left hand limit. Now let's see a right hand limit. So if you have a graph, and this is, it says f of x is equal to m as x approaches c, and f of x is equal to m as x approaches c from the right side. So here's an example. If you have this function over here, right, and this is c, right? Now this is the m value of f of x, right? And this is the, say, n value. Now at c, when you say that the limit of f of x as x approaches c is equal to m for this particular function, it's only true when you approach c from the right hand side, because if you approach from the right hand side, it approaches m. But if you approach c from the left hand side, right, it approaches n, because you cannot approach this particular you cannot approach m from the left hand side because, well, the function does not exist over here, right? And you cannot approach n from the right hand side because it does not exist over here, right? So this is how left hand and right handed limits work. Now let's discuss the continuity of a function. Now just to be clear, what continuity is basically, say you have this function over here. At this point, right, let's just say this is f of x, and this is this top point over here, this maximum is at L, and the x coordinate is at C, right? Now you can see that when you approach this function from the left hand side and the right hand side, you can see it approaches the same point, L, and that means that this function is continuous, right? Because there is no break. But although if you now look at this function over here, right, at this particular x point, let's say this is C as well, and let's say this here is M and this is N, right? You can see that there is a discontinuity at C, because from the left hand side it approaches N, but from the right hand side it approaches M, and this is the discontinuity at C. So this is just a brief explanation of what a discontinuity is. Now the question states that we have to discuss the continuity, so we have to tell if the function is continuous or discontinuous at x is equal to c. So in this particular example, c is equal to 2, so we have to find the continuity at x is equal to 2. Now the function itself, when x is less than or equal to 2, the function is 2x plus 5, but at x values greater than 2, the function is equal to 4x plus 1. So let's see what the solution is. First you have to find f at 2, right? Now because the question states that we have to find the continuity at 2, so first you have to find the value of the function at 2. Now you can see when x is less than or equal to 2, it is equal to 2x plus 5. So you'll use this equation, this expression, 2x plus 5. So you input, in place of this x, you input 2. So instead of 2x plus 5, you have 2 into 2 plus 5. And so you get 9. Okay, so that's your value of the function at x is equal to 2. Now you have to find the left hand limit. So the left hand limit means when x approaches 2 from the left hand side, what do you do? Well, you can see when the value of x is less than 2, you have again this expression 2x plus 5. So this means that the function is equal to 2x plus 5 when x approaches 2 from the left hand side, because it's less than 2. So you apply the limit, the left hand limit, into 2x plus 5. So again it is equal to 9. Now you have to find the right hand limit, because again I showed you the example. You have to find the right hand limit and the left hand limit to basically find a conclusion on the continuity. If the left hand limit and the right hand limit, if the left hand limit is equal to the right hand limit, that means that it is continuous. So let's see the right hand limit. So you're approaching 2, x approaches 2 from the right hand side. Now the function was equal to basically 4x plus 1 when x was greater than 2, right? And it was equal to 2x plus 5 when x was less than or equal to 2. Now approaching from the right hand side, you'd use this expression 4x plus 1, because it is the function value for when x is greater than 2. So you input the limit x approaches 2 in 4x plus 1, and that equals 9. So you can see that the left hand limit is equal to 9 and the right hand limit is also equal to 9. So just a second. So you can see that the limit as x approaches 2 exist because the left hand limit and the right hand limit are equal. So the limit of f of x as x approaches 2 is equal to 9, and so the function is continuous. Let's discuss the continuity at two different points of a function. This is the function given to us, and it says that we have to discuss the continuity at x is equal to 2 and x is equal to negative 2. So let's first do x is equal to 2, right? So at x is equal to 2, the actual value of the function is f of 2. And as you can see, when x is greater than or equal to 2, this also includes equal to 2, by the way, since we have to see x is equal to 2, the value of f of 2 is equal to this 3, right? Now let's discuss the left hand limits and the right hand limit. Remember, the rule is that continuity exists only if the right hand limit is equal to the left hand limit, right? So the limit as f of x approaches 2 from the left hand side is basically the limit of x squared minus 1 as x approaches 2. Why is it this particular one? Well, because when x is less than 2, the value of the function is x squared minus 1, which is why we've taken this one, x squared minus 1. So now that you input the limit 2, you get 3. So far so good, because that's what we have here. And now let's see the right hand limit. Now for the right hand limit, you'll use this 3 again. Why? Because when x is greater than 2, the value of the function is 3, and the right hand limit approaches from above 2, the value of x above 2. So you take 3, and so since 3 is a constant, you cannot apply this limit, and 3 will remain as it is, so it is equal to 3. Now you can see that the left hand limit is equal to the right hand limit, and so the limit of f of x as x approaches 2 exists, and that was equal to 3, remember? And so the function is continuous at x is equal to 2. Fairly simple. Now let's do x is equal to negative 2. Now you can see that at x is equal to 2, the value of the function, what is it? X is equal to negative 2. The value of the function is equal to 3x. Why? Because x is less than or equal to minus 2 over here. And when x is less than or equal to negative 2, you have 3x as the function. Since it includes the equal to part, you'll use 3x. So 3 into negative 2, that is negative 6. So f of negative 2 is equal to negative 6. Now, let's see the left-hand limit, right? So the left-hand limit, how do you find it? Well, when you approach x from the left-hand side of negative 2, you'll use this 3x again, because when x is less than negative 2, you have 3x as the function. So any value below negative 2, negative 3, negative 4, negative 5, anything that's approaching from the left of negative 2. So that means 3 into negative 2, you get negative 6. So far, so good, right? Now let's see the right-hand limit. Now for the right-hand limit, that means you have to go above negative 2. When x is greater than negative 2, you'll use x squared minus 1. Now instead of x squared, you'll input negative 2. So negative 2 whole square minus 1. And that is equal to 3. Now in this case, the left-hand limit, which is negative 6, is not equal to the right-hand limit, which is 3. Since negative 6 is not equal to negative 3, the limit as f of x approaches negative 2 does not exist, right? And that's because so f of negative 2 is not equal to the limit of f of x as x approaches negative 2, right? Because it's discontinuous. It does not approach the same value as from the left hand side and the right hand side both. It only approaches the value from the left hand side. It does not approach the value of negative 6 from the right hand side. So the function is discontinuous at x is equal to 2. I hope that helped. Now let's draw the graph of the equation. A very simple concept, but let's just conclude our chapter here on something a bit more visual. So it says we have to draw the graph of this equation, right? And basically, again, to draw a graph, you need to isolate the y value, because that is the y-axis and that is the dependent variable and x is the independent variable. So once you take x to the right hand side, it becomes the x squared to the right hand side, that becomes negative x squared. And then to basically just put y squared into normal y, take under root on both the left hand side and the right hand side. And so you get y is equal to positive and negative under root 9 minus x squared. And that's positive and negative because under root can be both negative and positive, but gives you the same value on both of them, right? Now the domain of this function is between negative 3 and 3. Why? Because once the value of x goes below negative 3 or above positive 3, the total value inside this under root sign will become negative, and that's an imaginary number. So for example, at x is equal to negative 4, well, what happens? The under root, it becomes under root 9 minus this x squared becomes negative 4 squared, and that becomes 9 minus 16, and that eventually becomes negative 7, right? You cannot take the under root of negative 7 because that becomes an imaginary number, and we're not dealing with that right now. So the real domain of this function lies between positive 3 and negative 3, right? So you have to now input individual values, individual integers between negative 3 and positive 3 into this equation. So when x is equal to negative 3, when you input it into this equation over here, the y value is 0, and so on and so forth. You get all of these values, but remember, you get both the positive and the negative value, right? So for example, if you input negative 2 into this particular, let's not take negative, let's take 0, right? So when you input 0 into this particular equation, that becomes 9 minus 0 square. So that becomes simply under root 9. But under root 9 is equal to both positive 3 and negative 3. Because when you square positive 3 or negative 3, you get the same answer, 9, right? So this, again, this is a very basic concept, but I'm just reminding why you have to be careful in these certain situations, right? So now that you have this, draw the graph, and this is a circle, right? Because when x is equal to 0, right, you have positive 3, so mark +3, and then you also mark -3. When x is equal to 1, which is this, you have to take both the coordinates at +2.8 and -2.8, and once you plot all of these points, you find out that it becomes a circle, right? So this is just a very simple example of graphing a function, and basically all you have to do is isolate the y and then input different values of x within the domain of x itself, and then just plot the values. Simple.